Now let's work out another problem. So it's given that this transfer function is e power s by s plus 1, okay, and the ROC is given to be the real part of s greater than minus 1. In other words, we can draw this ROC and there is a minus 1 here, and this is the ROC, this is sigma j omega. So the question is to comment on the causality and stability. The stability is very easy to comment because the ROC already includes the j omega axis, which means the system is stable. Now, is this causal? Now, the ROC is right-sided, but just because the ROC is right-sided, we cannot comment anything about the causality because first of all, this is not strictly a rational function also because we have e power s here. This is not a polynomial. So, it becomes difficult to comment about the causality here just by looking at the transfer function. So, what we will do is we will find the inverse Laplace transform. So, how do we find the inverse Laplace transform? So, once again we know that the Laplace transform of, let us say, some y of s is 1 by s plus 1. Then we know that the inverse Laplace transform actually for this is e power minus t u of t, right. So, what is the Laplace transform? So, if we have now the Laplace transform to be given by e power s y of s, then what is the corresponding inverse Laplace transform? We know that it is simply just y of t plus 1, right. Once again the properties. If there is a plus v here, then there is a here s times v here in the exponent, and that is exactly what we are going to utilize, which means this is e power minus the corresponding Laplace transform would be u of t plus 1. Now, how does this look like when we plot? Now, now e power minus t plus 1, when t is equal to minus 1, it takes value 1, and after that as t increases it decays and it goes like this. You just multiply these two functions together. So, what we would get is effectively this signal. So, this signal is our x of t. Clearly, the signal is non-zero for negative values of time, which means this is non-causal. So, as we saw in the discussion of the properties, just because the ROC is right-sided, we cannot comment anything about the causality here. Here the ROC is right-sided, it is stable, but if we find out the inverse Laplace transform, there are values for negative values of time which are non-zero, and hence this is a non-causal system. Now, this is an interesting example. So, here we have been given a transfer function s minus 2 divided by s plus 2 into s minus 5. Okay. Now, what are the possible ROCs that we can have here? So, there is a minus 2. So, here there is a 0 at 2. So, we can say that there is a 0 here at 2, and there is a pole at minus 2, and there is another pole here at plus 5. Now, this is a rational system. So, if it was a right-sided signal, then the ROC would be right of the rightmost pole. So, this is the first case, case 1, right-sided signal. So, clearly there are two poles in the ROC, which means the ROC cannot be the entire S-plane. If the ROC is the entire S-plane, there will be poles inside and the signal will be growing unbounded, so which does not make sense there. So, clearly we cannot consider that case, that is ruled out, and hence the impulse response also cannot be finite length impulse response. So, the other cases that we have here is right-sided, left-sided, or two-sided. So that's what we are going to consider. So the time domain impulse response is right-sided, that is case 1. In that case, the ROC would be the real part of S greater than phi. In this case, is the system stable or causal? Clearly, the system is not stable. Okay, because the j omega axis is not included in the ROC. Is this causal? Of course, it is causal because we consider the right-sided signal and the ROC is the right of the rightmost pole. So this is causal. Now let's consider case 2, left-sided. Just because the signal in time domain is left-sided, we can directly say that this is non-causal. What would be the ROC? It will be left of the leftmost pole. It will be less than -2. So let us say this is case 2. So this will be the ROC for case 2. Now is this stable or causal? Clearly this also does not include the j omega axis, so this is not stable. This is also not causal because this is a left-sided signal. So our property says that the systems are not causal. The third is two-sided. So what is the possible ROC for which the system can be two-sided? Remember, ROC can be left-sided or right-sided or a strip. The only thing that now is remaining is a strip between the poles. So you have to take the poles and they should border the strip that is of interest. So the strip that we have here is this region. So the ROC now is between the poles. Okay. And is this stable? Now finally we got a stable system. Is this causal? Definitely this is not causal because it is not a right-sided signal. So this is interesting. All we were given was a transfer function. Nothing was mentioned about the ROC. So we could get 3 different systems from 3 different ROCs, and there are 3 different configurations.